Welcome. Now we're going to talk about double or iterated integrals in this section and unit. So a double integral is just going to be dealing with an integral that has two integral symbols. And we can even have triple iterated integrals. And if you think about that word iterated or iteration, that just means repeating something. So we will integrate repeatedly 2 or 3 times. And you can have more than 3 integrals. I don't think we see anything like that in what we are learning in Calc 3, but we could have 5 integrals, for example. So let's review Calc 1. And what does Calc 1 tell us? Well, when we started learning about integrals in Calc 1, we had some function. And if we wanted to calculate the integral, that essentially meant we were calculating the area underneath the curve. And hopefully you guys remember what we did was we created a bunch of different rectangles. We developed a Riemann sum to help us approximate that integral. So that was our development of our integral definition, I should say. So what is that integral? How did we find that area under the curve? Well, we said we're going to look at the limit as n approaches infinity of the sum from k equals 1 to some nth value of, I don't need that parenthesis there, f of x sub k times some delta x sub k. So we have a function output value that gives us the height at each of these points that we were choosing. And then we've got this delta, which is that horizontal distance or my change in x. So this was my limit definition. And essentially we were saying, well, n goes to infinity. So that means we would be summing infinite rectangles. And as we sum infinite rectangles, the width of these spaces becomes smaller and that approximation approaches the exact value. This sub k here, this is just talking about, we could choose a left hand or a right hand, a midpoint, a lower, an upper. And eventually we learned it really didn't matter where on each interval we chose that k value. So we could choose k to be anywhere on each of these little intervals. And that's all that sub k is saying. Okay, so this Riemann sum definition or the limit definition of an integral, that built us towards understanding that this represents the integral from a to b of some function x. All right, so essentially what we did is we took the interval, we partitioned it into a lot of little subintervals, and as those subintervals became very small, we were able to accurately approximate or approach that exact value for this integral. So single integrals, an integral with just one integral symbol, that represents area under the curve. So now we're dealing with surfaces, and if we take that area and we multiply it by another dimension, what we're going to be finding is that these double integrals, they tell us information about volume. So let's think about what we are doing here. I'm going to do kind of a volume example before we get into our definition to help you understand what all of this is supposed to look like. So what we're going to do is we're going to be given a function z, which is a function of two variables, f of x, y. And it's going to be continuous and non-negative, so it just means that this surface is above my xy plane on some region R. So normally we would have said an interval I. Here we have, instead of just an interval, we have a region of ordered pairs, x and y points, in the xy plane. So we're going to look at finding the volume of some solid that is enclosed between my surface, z, and the xy plane on the region. So what does this look like? So let's think about drawing this. Here are my axes. So essentially we've got some surface here up in space. That is my Z. And looking down here on the XY plane, we might have some region. In this situation, it's a rectangular region. We'll call this guy R. So there's my region R. And the idea is if I take R and I map it up to Z, right? If I take this and map it up there and draw this beautiful little diagram, there's kind of a parallelepiped or a rectangular prism that's formed between the XY plane and that surface, right? So we're mapping R up to my surface and we're going to find the volume. So what are the steps? What are we going to need to do here? So the first thing we do is we take that R and we're going to partition my region R, partition R into sub-rectangles. So what that means is if this was my whole R, this is all of R here, I'm going to take it and maybe divide it into 8 equal sized rectangles. So the second step would be, well, we need to choose a point. I'm going to call that X sub K star and Y sub K star on each rectangle. So we're choosing a point in each of these. I could say I wanted to choose the midpoints. I could say I wanted to choose the upper right-hand corners. And this star notation, that's just telling me I can just choose the most convenient point. We're choosing one point anywhere on these rectangular spaces, these sub-rectangles that I've partitioned out inside my original region R. And so at this point, we would take each of these sub-interval rectangles, and we'd have 8 of them, and I would map each of these 8 rectangle heights up to that surface. So part 3 here, we're going to map each of those XY points onto that surface Z. And so each time I take one of these points and I map that up there, I have an area of this little rectangle multiplied by the height. I'm going to have all of these different rectangular prisms or parallelepipeds. So I'm forming a bunch, in this case, because I've drawn 8 rectangles, we'll form parallelepipeds, 8 parallelepipeds. I cannot spell this, pipeds. All right, so those are these rectangular prisms. And we can do this for all of the rectangles. All of these rectangular prisms. And we can find the volumes. So we'll find the volume for each. And so the volume is going to be approximately that base area times this height that we find when we map the point up to the surface, or rather the volume is approximately delta A, that base area. Normally we would say delta X in our definition because those are our sub-interval widths, but now we have sub-rectangle areas. And so we take that area, delta A, that base area, and we multiply it by the output, the z value, which is x sub k star y sub k star. And, just to reiterate the star, normally when we choose these points, you know, when you're learning this, we say, okay, use the lower bound or the lower height or the left side or the right side bound or a midpoint bound. But the star says I can choose that point anywhere on the rectangle, essentially. It doesn't have to be the left or the right, and I'm still going to get a good approximation. So that's what this star means. So we've got the base area times the output function value, and that gives me the volume of one rectangular mapping. So if I've done this for all of my rectangles, then I can sum them, and we can kind of assume here that the volume, right, this is the volume for one rectangle. So the volume for that entire region is going to be the sum of all those rectangles. So we would say the limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k star times y sub k star times delta a sub k. So this is sort of my formal Riemann sum definition for volume. And of course, as n becomes infinitely large, that means I have made infinite more points in my rectangular region R, and each of those parallelepipeds, the base area is becoming smaller and smaller, so we have more and more of them. And the more rectangular regions, the smaller those base areas, the more of them we'll have, the more accurate this approximation by adding all of these sums is. So just to reiterate, and I've pulled in here this picture from the text because I think it looks a little nicer. So we have this green surface here, and we want to find the area on this rectangular region between A and B on the x-axis, and you can't see it, but there's a C and D here on my y-axis. So you see my rectangular region is down here below, and we're mapping that entire region up, but we're making all of these little sub rectangles on the region, and we can draw a lot of those. And of course, the smaller we make them, the more accurate it's going to be when we consider our approximation. Let me pull this visual in for you. So if we took our rectangular region R and we divided it into 16 sub-rectangles, and we mapped each of those up, it gives us a decent approximation of that surface. But notice as n becomes infinitely larger, or n even just becomes larger, we start to get a better approximation of what that surface is. And if we look at n, say, equals 256, you can see how this would give us an even closer approximation. So creating an infinite quantity of these rectangles, they're all going to have a very small base area, and that's how we can find that value for the integral. Okay, so this is kind of our formal definition, and I think it's important for you to understand what we're doing. Now, we have a couple of things we want to keep in mind. So if my surface has both positive and negative values on that region, what do you remember from Calc 1? When we calculate the area beneath a curve, if we're above the x-axis, that's going to be positive, and below the x-axis, that region would be negative. So that would mean the volume is going to be a difference in that volumes between the region, considering the parts of the surface above and below the plane. So the area above, we would have a positive minus some negative. That's going to give me that total volume. this limit definition, the limit of the sum of all of these z's times xy areas on that region, we're going to redefine this and say, well, volume equals the double integral evaluated across the region. So we have x values and y values that define this rectangular surface in the xy plane of my function f of xy integrated with respect to the area. And the area is a product of x and y. So as long as this delta A sub k is approaching 0 when n is approaching infinity. So as n becomes increasingly large, these areas become much smaller. This works. So let's look at a really basic example. For this example, we're going to estimate the volume of the solid that lies above this square region, region R. So this capital R means the region. We're saying that x is from 0 to 2, and my y values are from 0 to 2. That creates a square in that first octant. So above that region and below my surface. And we're going to divide this into 4 equal squares. So we're going to take R, 0 to 2 by 0 to 2, and divide it into 4 squares, all of equal side. And we're going to choose the same sample points. We're going to choose those sample points to be the upper right corner. And of course, I stated that sample point could be anywhere on that partitioned sub-rectangular area, but if we all use different sample points, we'll all get slightly different answers. And so for this reason, we're all going to do it the same way. So what we're looking at here is we want to look what that volume is between this region and my surface. My surface is z equals 16 minus x squared minus 2y squared. And you guys should recognize this. This is an elliptic paraboloid. So if we think about what this graph looks like, and I'm only going to draw the first octant here, but we have some elliptical paraboloid. So it's coming down like this, and it is curved like that. We have a height up here of 16. Right, that's the y-intercept. This is an elliptical paraboloid opening down. I said y-intercept, I mean my z-intercept. We're on the z-axis. And so what is my region? My region is this square in here, coming out to this ordered pair 2, 2. So we got 2 on the x-axis and 2 on the y-axis. So one of the first things we always want to do is we want to visualize what our surface is. And then we want to graph our region R. So I've got 0 to 2 on my x-axis, 0 to 2 on my y-axis. That creates a square region here. And we can divide that into 4 equal squares. So if we use the upper right-hand corner, this would be R11, x equals 1, y equals 1. This region will be R, that's x equals 2, y equals 1. And I've got region here, 1, 2, and then a region here, 2, 2. So I can calculate the area of each of these regions, and of course the area is length times width, 1 times 1, which is 1. And then I'm going to calculate my heights based off of these points, the point in this corner where this rectangular region comes up and touches my surface. So by definition, that volume is going to be this double integral over the region R of this function 16 minus x squared minus 2y squared dA. That volume, that would be the way I would set up my double integral. That's going to be approximately the volume of the 4 parallelepipeds. I just want to cut that last consonant out pipeds, right? So I can shoot up, I'm going to have 4 different parallelepipeds that are going to go up and touch my surface. And it's starting to look really messy when I draw these little rectangles in here, but I think you guys have the idea of what I'm saying. We draw these rectangles up, they're all touching the parallelepiped based off of these corners. If we add all of those volumes together, it's going to be approximately the volume of this elliptical paraboloid. So what would that mean? That's going to be approximately the sum of those outputs, those f of x, y, output, my z ordered pairs, times that area of each of those bases. Or in more layman's terms, my sum of all my heights times my base area. So that is approximately, well, my base area is going to be the same for all of them, 1 times 1. So there's my base area times f of 1, 1 plus f of 1, 2 plus f of 2, 1 plus f of 2, 2. So these are all my output, my z values, and I just plug each of those ordered pairs into my function. Of course, my base area, 1 times 1 is 1, so I don't really need that there. And my outputs I get are 13, 7, 10, and 4. That gives me approximately 34 for the volume. Of course, this is a underestimate because all of those rectangular regions are going to be below the surface. They're all going to be stopping a little bit below. All right, now we're not going to use that definition a lot. I'm not going to make you use the long definition, but I think it's important for us to understand how it works. So that's it for this video. I know it was long, but I couldn't really break that into pieces. Email me if you have any questions.